Today, I'd like to discuss some formulas for calculating integrals. To help you visualize these formulas, I'll present them using geometric intuition. I'll assume that you're comfortable with derivatives and that you understand at least the basics of what an integral is. Simply put, if you know the material that's covered in a Calculus 1 course, then you're good to go. Also, this video is inspired by 3 Blue 1 Brown's Essence of Calculus series, and it can be watched as a supplement to that series. However, if you want, you can instead just watch this video on its own. Don't worry, you won't miss any important context. Let's kick things off with a simple integral. We want to integrate sine of x over x dx from the lower bound 2 to the upper bound 2. Just to find our bearings, we'll draw a graph to represent this. Sine of x over x, with the area under the curve from x equals 2 to x equals 2 representing the value of the integral. But what's weird about this is that since the lower bound and the upper bound are the same, there is no area. Rather, to be more precise, there's an area of 0. This gives us our first integral rule. If the lower bound and the upper bound of an integral are the same number, then the value of the integral is 0. By the way, I admit that I pulled a bit of a prank on you with the function I chose to integrate, sine of x over x. The most common way to calculate an integral involves finding an antiderivative of whatever function you're integrating, relying on the second fundamental theorem of calculus. Sine of x over x does have an antiderivative, but it's not one that can be expressed by combining the usual functions and operations. The arithmetic operations, exponentials, logarithms, trig functions, that kind of thing. This is a special kind of antiderivative. It's called a non-elementary antiderivative. It's kind of crazy how this can happen, isn't it? For our next integral, we'll use something called a piecewise function. This is a function that's defined in multiple different pieces in different parts of the function's domain, where each piece of the function has its own rule. For this piecewise function, let f of x equals 1 if x is less than 0, and cosine of x if x is greater than or equal to 0. What's the integral of this function from negative 2 to pi over 2? Again, it helps to graph this out. On the x is less than 0 side, we have a flat line representing the value 1. On the x is greater than or equal to 0 side, we have a cosine wave. The area under the curve from x equals negative 2 to x equals pi over 2 is what we need to calculate. We can do this by slicing the area into two pieces. One piece goes from x equals negative 2 to x equals 0, and the other piece goes from x equals 0 to x equals pi over 2. We can now calculate each area using a separate integral, and then we can add the values of the integrals. For the first integral, we use the x is less than 0 piece of the function, so we substitute f of x equals 1. For the second integral, we use the x is greater than or equal to 0 piece of the function, so we substitute f of x equals cosine of x. We're left with integrating the constant 1 from negative 2 to 0, and then integrating cosine of x from 0 to pi over 2. A quarter turn along the unit circle, if you will. I've already made my point here, so I'll choose not to complete this calculation. If you still want the answer, I'll leave it as an exercise for you. For now, we can state the general integral rule. If you have an integral that goes from a to c, then you can choose some value b in between a and c. After that, you can split the integral into two integrals, one going from a to b, and the other going from b to c. Adding the values of these two integrals gives you the value of the original integral. For integral problem number 3, before I say the integral that we want to solve, I'll actually start by saying the value of another integral. Let's say f is a function such that the integral of f of x dx from 2 to 6 is equal to 15. For simplicity, we'll assume that f has a positive value on the entire closed interval from 2 to 6. I've drawn a diagram to show what that might look like. However, I won't actually tell you what the function is. Now, what's the integral of f of x dx from 6 to 2. You might not be used to an integral where the lower bound is greater than the upper bound, but it's a real thing. If we want to solve this problem, we'll need to recall how an integral is actually defined. At its core, an integral is about summation. We can slice up the area under the curve into a bunch of thin rectangles, where each rectangle's signed height is f of x, and its signed width is dx, which is some tiny nudge in x. The signed area of each rectangle is f of x times dx. If the lower bound of the integral is less than the upper bound, then to get from the lower bound to the upper bound, we have to take positive tiny nudges. That means that dx has to be positive. On the graph, that looks like going from left to right. However, if the lower bound is greater than the upper bound, then this is reversed. To get from the lower bound to the upper bound, dx has to be negative. With that in mind, let's go back to the integral that we need to solve. When we slice up the integration area into thin rectangles, does each rectangle have a positive or negative signed area? If f of x is positive and dx is negative, then f of x times dx, the signed area of each rectangle, must be negative. The integral sums up all of these negative values, giving us a negative total. This must have the same magnitude as the original integral, but the opposite sign. So that gives us our answer, negative 15. As another exercise for the viewer, consider the following. Remember that a negative times a negative is a positive. If f of x being positive and dx being negative means that f of x times dx is negative, then what if f of x is negative and dx is negative? Will f of x times dx be positive or negative? As a result, what does this say about integrating a function with negative values in the negative direction? Now that we've seen an example, we can generalize it into an integral rule. Basically, the rule states that you can swap the lower and upper bounds of an integral as long as you attach a minus sign in front. In other words, the integral from b to a is the negative of the integral from a to b. When you integrate in the negative direction, the area above the x-axis is counted as negative, whereas the area below the x-axis is counted as positive. It's kind of like playing a video backward, undoing what happens when the video is played forward. That completes the integral rule trio. Keep these 3 integral rules tucked away in your mind because they'll prove highly useful for manipulating integral expressions. Before we move on, I'd like to share how each of these rules connects to the second fundamental theorem of calculus, or FTC. As a refresher, this theorem is as follows. To evaluate the integral from a to b of f of x dx, you can find some function, big F, which is an antiderivative of small f. For now, I'll refer to small f as just f. Then the value of the integral is big F evaluated at the upper bound b, minus it evaluated at the lower bound a. If we apply this to the first integral rule, we get big F of a minus big F of a. Anything minus itself is 0, so the integral is equal to 0. So far, everything checks out. For the second integral rule, let's start with the right-hand side. The first integral becomes big F of b minus big F of a, whereas the second becomes big F of c minus big F of b. So the whole thing becomes the difference of big F of b and big F of a plus the difference of big F of c and big F of b. We can get rid of some of the parentheses, and then we notice that there's a big F of b and a minus big F of b, so those cancel out. Reorder the terms and then apply the fundamental theorem of calculus again. The integral from a to c of f of x dx is equal to big F of c minus big F of a. So we can apply that equality the other way around. Again, so far so good. Now for the third integral rule. I'll once again start with the right-hand side. The integral is equal to big F of b minus big F of a, and we have to remember to attach a minus sign to the whole thing. When we distribute the negative, this becomes negative big F of b plus big F of a, which can be reordered as big F of a minus big F of b. Again, use the fundamental theorem of calculus. This is the same as the integral from b to a of f of x dx. So we've verified all three rules using the FTC. In fact, you'll notice that rule number 2 in particular was made stronger. We never had to assume that b is between a and c, so we can remove that restriction entirely. However, notice that using the algebraic manipulations alone wouldn't have given much intuition for these rules. We already made sure that the rules feel good through other methods involving graphing. If anything, I hope not just that the FTC made you feel better about these three rules, but also that the rules made you feel better about the FTC. Next, we'll look at some rules for integrals that basically reverse the rules for derivatives. Let's start by trying to integrate x dx from 0 to some upper bound, which I'll label as big X. For brevity, I'll keep referring to little x as just x. To think about the integral as a function of big X, we'll use it to define the function big F of big X. As an example, you could plug in 4 for big X, and then the integral would go from 0 to 4. Again, let's assume that you don't know anything about the fundamental theorem of calculus. How do you find the value of this integral? It turns out for this particular problem, just using a graph is the most straightforward path to the answer. We can graph the function x, and then choose some number big X to be our upper bound. Then, in the interval in between the lower and upper bound, we can approximate the integral using a bunch of rectangles, where each rectangle has a signed area of x times dx. For smaller and smaller choices of dx, we get closer and closer to the true value. The shape whose area we want turns out to be a triangle, one whose base length is big X, and whose height is also big X. That gives us our answer, 1/2 times big X squared. Going back to the example, big X equals 4, if we just plug that in, we get 1/2 times 4 squared, which is equal to 8. Next, we'll make this integral a bit more general. Instead of the lower bound being 0, we'll make it an arbitrary constant, a. Let's have this integral define a new function of big X called big G of big X. I'll graph out what that looks like. To calculate the area of this shape, we'll once again consider this big triangle with an area of 1/2 times big X squared. However, we now need to subtract off the area of this little triangle. Its base length is a, and its height is also a, so its area is 1/2 a squared. Subtract the second value from the first value, and you have the answer. With this function in mind, let's connect it back to the FTC. What if we take the derivative of big G of big X with respect to big X? Let's think about nudging big X by some tiny amount, d big X. This causes some little change to the value of the integral, d big G of big X. Geometrically, this tiny change is shown by a little sliver. In this case, the sliver is a trapezoid. If d big X is tiny, then we can pretty much consider this sliver to be a rectangle. So its area is big X times d big X. To obtain the derivative, divide both sides by d big X. So the derivative of the integral gives you back the original function, just with small x renamed to big X. And that's exactly what the first fundamental theorem of calculus tells us. Derivatives and integrals are inverses of each other. Also, if the lower bound of the integral is some constant a, then the derivative of the integral doesn't care about what a is. We can adjust a to any value we want, but the derivative of the integral will stay the same. Now that we've looked at the derivative using geometry, let's instead try taking the derivative using algebra. Earlier, we found that big G of big X equals 1/2 big X squared minus 1/2 a squared. So the derivative of big G of big X with respect to big X is the derivative of 1/2 big X squared minus 1/2 a squared with respect to big X. We'll split this derivative into two terms using the sum rule. For the first term, using the power rule, 1/2 big X turns into big X. For the second term, remember that a is just a constant. So minus 1/2 a squared must be a constant term. Using the constant rule, its derivative is 0. The whole thing becomes big X plus 0, or simply big X, which is the same answer we got before. Now let's move on to our next problem. This time we'll try to integrate x squared. Unfortunately, in this case, the graph won't be of much help in evaluating the integral. If you graph the x squared function, you get a parabola, and it's not immediately obvious how you would find the area under a parabola. Instead, we'll find some other way to represent this integral. We'll start by representing the quantity x squared dx. Consider a thin square sheet where the side length of the square is x, and the thickness is dx. The volume of the sheet is x times dx, or just x squared dx. Now we just need a bunch of these sheets for values of x going from 0 to big X, and summing up their volumes will give us the answer. I'll draw all of these square sheets, lining up their corners along the x-axis. Just as an example, I've picked big X equals 3, and I'm using dx equals 0.25 for now. If we look at the square sheet at x equals 2, then substituting our values for x squared dx gives us 2 squared times 0.25, which is equal to 1. So this particular sheet has a volume of 1. The volume of each other sheet is calculated in a similar way. Now that we have this set up, we allow dx to approach 0. When we do, we get an overall solid in the shape of a square pyramid. It has a square base, and each vertex of the base is connected to an apex point. How do we find the volume of this solid? There's a formula for the volume of a pyramid, which you can apply if you know it. However, that formula is usually proven using an integral, so this is kind of cheating. In our situation, without relying on the formula, we can use a clever trick. If you take 3 separate copies of this pyramid, you can fit them together into a cube. The volume of this cube, with all 3 pyramids combined, is big X cubed. So, the volume of each pyramid must be 1/3 big X cubed. This is the volume we were looking for, so we have our solution to the integral. Just to use the big X equals 3 example, when we plug that in, we get 9. So the integral from 0 to 3 of x squared dx is equal to 9. Like before, we can undo the integral by taking a derivative. Let's use big F of big X to denote the integral. If we take big X and nudge it by some tiny amount, d big X, then the pyramid's volume changes by some amount, d big F of big X. This added volume takes the form of a frustum. Yes, that's actually what this shape is called. If d big X is small enough, then the frustum basically looks like a square sheet, and its volume is big X squared d big X. Divide both sides by d big X, and we find that the derivative of big F of big X with respect to big X is equal to big X squared. Algebraically, we can check this using the power rule. Remember, this integral is equal to 1/3 big X cubed. To take the derivative of that, apply the power rule. Big X cubed turns into 3 big X squared. So 1/3 big X cubed just turns into big X squared. This matches our earlier answer. One last thing I'd like to do with this integral is apply graphical intuition. Like I said before, looking at graphs wouldn't help you evaluate the integral, but it'll still be a nice gut check. I've graphed the x squared curve, and we'll look at the area calculated by the integral for different values of big X. We'll start by letting big X be equal to some very negative number, say -6. Looking at the area under the x squared curve going from 0 to -6, the function has positive values in this interval, but we're integrating in the negative direction, so the overall result is negative. Indeed, if we calculate big F of -6, we get -72, which is negative like we expected. I've graphed big F of -6 equals -72 in blue. Now imagine gradually sliding big X toward the right, in the positive direction. As we do, the area under the curve gradually gets less negative, so big F of big X also gets less negative. That is, its value is increasing. However, the increase slows down as we get closer to 0. In fact, that speed is directly determined by the value of big X squared, which is the function we're integrating. That just comes straight from the fact that big X squared is the derivative of 1/3 big X cubed, because a derivative measures a rate of change. When big X equals 0, the area under the curve is 0, so big F of 0 equals 0. Then, if we just keep increasing big X, the increase in big F of big X will speed up again. Just as 2 more examples, here's big F of 3 equals 9, and here's big F of 6 equals 72. Looking back at the last 2 sections, we first integrated x dx, and then we integrated x squared dx. To follow those 2 examples, let's find a general rule for the antiderivative of x to the n for some constant n. Can we proceed geometrically like we did before? The answer is technically yes, at least if n is a natural number. However, it requires thinking about hypercubes and hyperpyramids in higher dimensional geometry. Don't get me wrong, I love higher dimensional geometry, but I don't think it's the best way to proceed here. Instead, we can approach this algebraically. You might sense that there's some kind of connection to the power rule for derivatives. So let's write out what it looks like to take the derivative of x to the m for some constant m. In fact, if you'll trust me for a moment, it'll actually be a bit nicer to swap the sides here. Then, if m is not equal to 0, we can divide both sides by m. On the right, I'll write this as multiplication by 1/m, which is really the same thing. Using the constant multiple rule for derivatives, we can take this factor of 1/m inside of the thing we're taking the derivative of. Now let's take the antiderivative of both sides, writing it using an integral symbol. On the right, the antiderivative cancels with the derivative. We have to tack on an arbitrary constant c, because the derivative of a constant is always 0. Finally, to get x to the n inside of the antiderivative, we'll substitute n plus 1 for m. So that's how you take the antiderivative. Add 1 to the exponent, and then divide the entire term by the new exponent. This is often called the reverse power rule, because it basically undoes the power rule for derivatives. Using the reverse power rule, you can take the antiderivative of any polynomial, which can definitely come in handy. There is a bit of a snag. This rule fails if n is -1, because you have to divide by 0. This corresponds to the m equals 0 case we excluded earlier. So how do we take the antiderivative of 1/x? If you remember that the derivative of ln of x is 1 over x, then you can just flip that around. The antiderivative of 1 over x is ln of x plus some constant. Well, almost. ln of x only allows positive values of x, but 1 over x is defined for all non-zero values of x, including negative values. To fix this, we can say that if x is less than 0, then the antiderivative is ln of negative x plus some constant. Because we're negating some value of x that is itself negative, the result is a positive number inside of the natural logarithm. You can verify that taking the derivative still gives you 1 over x. Let's also check if this makes sense with our graphical intuition for derivatives. Here, I've graphed ln of x if x is greater than 0, and ln of minus x if x is less than 0. For simplicity, I've let the added constants be equal to 0 for now. Starting on the positive side, let's pick x equals 1 for example. At x equals 1, the ln of x curve should have a slope of 1 over 1, which equals 1. Going toward the right, 1 over x is closer to 0, so ln of x shallows out. At x equals 4, the slope is 1 over 4. For the negative side, let's pick x equals minus 1. At this point, the ln of minus x curve should have a slope of 1 over minus 1, which equals minus 1. Going toward the left, 1 over x is closer to 0. The slope should remain negative, but get more shallow. At x equals minus 4, the slope is 1 over minus 4, which is minus a fourth. We can write the whole antiderivative using piecewise notation, remembering to include the added constants. Speaking of those constants, we're allowed to use a different constant for each piece. Say c1 for x is less than 0, and c2 for x is greater than 0. Even if they're not the same constant, the derivative of this function will still be 1 over x. The pieces are disconnected from each other, so they can be shifted independently. However, note that the antiderivative of 1 over x is usually rendered as ln of the absolute value of x plus c. The absolute value function flips the sign of a negative number, but leaves a positive number unchanged, just like we want. This doesn't quite achieve the fullest generality, but it's written this way mainly for convenience. For the final integral of the video, and probably the most difficult, let's tackle some trigonometry. How do we integrate cosine of theta d theta from 0 to big theta? Like before, this will come down to finding some way to represent cosine of theta times d theta, the amount that we're summing up. First things first, since this problem involves trigonometry, we'll be working with angles. This is a hint that it'll be useful to draw the unit circle, the circle centered at the origin with a radius of 1. Specifically, if you walk a distance of theta units along the unit circle, say 0.6 units, that means you've walked theta radians around the center of the unit circle, say 0.6 radians. The bounds of our integral are the angles 0 and big theta, so let's draw them on the unit circle. For the lower bound 0, start at the rightmost point on the unit circle, then walk 0 units counterclockwise along the circle. In other words, don't move at all. Mark this point as the 0 angle. As for the upper bound, let's say that big theta equals 1.2 for the sake of example. Starting at the rightmost point on the unit circle, walk 1.2 units counterclockwise along the circle. Mark this point as the big theta angle. The interval that we're integrating over is represented by the arc of the unit circle from the 0 angle to the big theta angle. Slice it into a bunch of tiny d theta steps, just like we did for all of our previous integrals. The only remaining problem is that we still haven't figured out how to represent the quantity cosine of theta times d theta, so we'll look at that now. Let's review the right triangle definition of cosine. Consider an acute angle theta in a right triangle. The cosine of that angle is equal to the adjacent leg divided by the hypotenuse. Rearranging this equation, this means that the length of the adjacent leg is equal to cosine of theta times the hypotenuse. Based on this, wouldn't it be nice if we could construct some right angle where the hypotenuse is d theta? That way, cosine of theta times the hypotenuse would be cosine of theta d theta, which is the value that we're trying to represent. This can be done with one key observation. For some value of theta, let's say theta equals 0.6 for example, draw that central angle in the unit circle. Then, from that point on the unit circle, draw a vertical line segment to the x-axis, creating a right triangle. At the chosen theta value, consider the tiny d theta step. If it's small enough, then it basically looks straight. I'll draw this tiny right triangle here, using d theta as the hypotenuse. Zooming in on the tiny right triangle, you might notice that it and the large right triangle seem to be similar triangles, that is, triangles with the same proportions. To prove this, notice that the yellow angle in the large triangle is between a horizontal line and a radius at theta, whereas the light blue angle in the small triangle is between a vertical line and a tangent line at theta. So, those angles must have the same measure. Also, the two triangles share a right angle measure. By angle-angle similarity, we conclude that the two triangles are similar. Now, do you remember the way that we represented cosine of theta times d theta earlier? As it turns out, we found a tiny right triangle that looks exactly the same. The vertical side of the tiny right triangle, colored in purple, has a length of cosine of theta times d theta. So we've managed to fit cosine of theta times d theta into our diagram. Now, we just have to draw tiny right triangles for all of the d theta steps, from 0 to big theta. Now that we have all of these vertical sides, still colored purple, how do we sum them up? We can translate these sides so that they all fall into the same vertical line segment, which I'll now color in blue. The length of this blue line segment is the same as the height above the x-axis of the big theta point on the unit circle. By definition, that height should be equal to sine of big theta. So we finally have the answer to our integral. Just like before, we'll take the derivative of this integral. For simplicity, let the integral be denoted by big F of big theta. To take the derivative of big F of big theta, imagine nudging big theta by some tiny amount, d big theta. This causes the value of the integral to change by some tiny amount, d big F of big theta, shown in purple. The derivative is the ratio of these tiny differences, d big F of big theta over d big theta. Looking at the tiny right triangle, d big F of big theta over d big theta is the same thing as adjacent over hypotenuse, and adjacent over hypotenuse is the same thing as cosine of big theta. So everything works out in the end. When I made this video, I set out to derive a bunch of rules that you can use for calculating integrals. However, that wasn't the only purpose of this video. If it were, then I could have saved myself a lot of trouble by just blindly applying the fundamental theorem of calculus over and over again. In reality, there was a deeper goal at play in this video, trying really hard to convince you that the fundamental theorem of calculus. This theorem gets its highly pompous name for good reason. The connection between derivatives and integrals is the core idea of calculus. My fear is that too often, this connection is reduced to nothing more than a computational tool. And that's a real shame, because I believe that when you truly feel this concept deep inside your heart, the underlying beauty of calculus shines through in all its glory.